Kia ora everybody, Mr. Bowman here. In this video, our learning objective is in red and we're looking at the polar form of complex numbers. Our starting point today is getting an understanding of the key concepts. So I think prior to the polar form, you should have learnt a little bit about the rectangular form of a complex number. So a rectangular form, your teacher may have described it, for example, as a plus bi. And an example of what that looks like, for example, a, that's your kind of real component. So that might be, let's say, 3. And bi would be the imaginary part, so let's say that's minus 2i. So that's the form you're probably more familiar with dealing with. And the cool thing about this form is we can actually plot this and we can kind of visualize what these imaginary numbers look like by plotting them on our Argand diagram. So let's write that down here. So Argand diagram, hopefully you've heard that phrase before. So that's the Argand diagram. The x-axis, in terms of the Cartesian plane, this is now going to refer to the real element of our complex number, which is going to be a, or 3 for the example we're dealing with. And your y-axis going up and down, that's going to be the complex plane. So that's going to be the imaginary part. So imaginary part of that, and that's always in terms of I, isn't it? So what we're looking to do here is we're looking to plot, just to kind of visualize what this imaginary number looks like. So 3 is the real number, so it's kind of going to be over here along the real axis, and then we're going to go down to negative 2i. So that number we've drawn there, 3 minus 2i, the example we did, would be represented by the dot over here. And if we connect that with the origin, so let's draw a line connecting the origin to that point, which again is 3 minus 2i, we can actually visualize what that rectangular form or what that imaginary number looks like, which is ironic given the name, it's imaginary. The fact we can see it is an interesting point. So hopefully that's some background knowledge about the rectangular form, which you're maybe familiar with. We've linked it with the Argand diagram, and the point of this video is, well, this polar or this rectangular form we've got there, we can actually swap it back and forth between another form of complex numbers. So the next one we're going to look at is called the complex form. Oh, sorry, not the complex form, the polar form. And the formula, the generalization we have this, is going to be R cis I, or cis angle. So this R here, well, I suppose before we get into the R and the angle, so this polar form actually relates to the line that we've drawn here. So the visualization of the imaginary number, we can describe it in addition to the rectangular form based on the real and imaginary part, we can describe it visually what it looks like. So the R that I started talking about before, that's actually going to be the length, or how long this imaginary number is. And we also call that the modulus. So you may describe that, so that's called the modulus. This next one here, that's actually the angle, and I'll get into a bit more about the angle soon. That's the angle created by the line, and we call this the argument. And as I said, there's a lot more to the argument or the angle than known. So I guess the first thing to note is this angle is in relation to the x-axis or the real axis only. And I do want to note it's the positive part of that. So I'm just going to highlight that on our Argand diagram above. So this part here of the axis, so the angle in between this part and the imaginary number, that's often referred to as the argument. But the diagram I've drawn there is a little bit misleading because the angle is referred to in an anti-clockwise way only. Anti-clockwise only. So going back to my diagram, that angle I drew kind of in between here, that there would actually be a negative angle because it's going in the opposite direction. That's going clockwise, isn't it? So technically our angle is going to be all the way around here, all the way around here, up to my imaginary number. So technically that's the positive version of that. Now there's going to be even more to the angle that we need to know about. So again, drawing a line on the positive section of the real axis. Hopefully you remember, if we do a full revolution, that's typically 360 degrees. But because this is year 13 calculus, we need to deal with radians. So 360 degrees, in radians, that there is going to be 2 pi. So we need to actually be dealing with radians, and we need to know how this works to solve some of the problems that we're dealing with. So for example, if we go from here up to here, because we've got quarters, that's a quarter of my diagram, there's another quarter, there's another, all 4 quarters would be 2 pi. This rotation that I identified before, that's actually going to be 1/4 of 2 pi, which is pi over 2. If I did, a half revolution up to here, well, that's going to be 1/2 of 2 pi, which is just pi in this case. And again, if I do a 3/4 revolution, well, that's going to be 3/4 of 2 pi, which is going to be 3 pi over 2. And then finally, start to finish, if I go all the way around to the end, that there is going to be 2 pi. It's the full 360. So knowing half pi, which we had up here, pi, 3.5 pi, and then, so not 3.5, 3/2 of pi, and then 2 pi, we may need to use that information to calculate the modulus, or to calculate the argument to find our polar form. So we know a bit about the theory now, so let's get into some easy examples. So you'll see everything we've got in the questions here, from easy, medium to hard, they are all in the rectangular form. So we now need to think about the polar form. So I'm going to write down our definition or our formula. So it's going to be r cis angle. Remember, this here was the length, this here was the angle. So let's find that out. So the first question we got here is A. So our rectangular form, it's -2, but don't forget there's no i's there, so that's actually plus 0i. So we're going to start by visualizing this. Let's plot this on our Argand diagram. So we've got -2 over here, and then there's 0 i's, so that means that point doesn't go up and down. Hopefully you can see that there. So the length we're dealing with, I think the length will be quite clear. Do you see between here and the origin? Well, that's just 2 units long, isn't it? So it's nice and easy because it's a nice flat a flat horizontal line. Makes it easier. So in our case, r is actually going to be -2. So right, also +2 because it's a length. You can't have a negative length. Now the angle, don't forget the angle is, so there's our imaginary number, and we're dealing with the positive part of the real axis. So how do we go from here to here? What angle do we flip it at? And this looks like it's been flipped 180 degrees. And remember, we have to go anti-clockwise. And we talked about this. This is going to be 1/2 of 2 pi. So we talked about that in the previous section, which is just pi. So our argument is just going to be pi. So like that, we've got the modulus and we've got the argument. We can now use this to get that polar form. So r is going to be 2, so it's going to be 2 cis pi as our angle. So just a reminder, this pi sometimes might be some messy decimals, but a rounded version or the exact version in terms of pi is all good. So moving on to B, which is over here. So what's the polar form of 4i? So reminder, 4i, so this real element will be 0, and then your imaginary element will be 4i. So it's going to be 0 here, so it's going to be something on the y-axis, and it's going to go all the way up to the top here, so that there would be 4i, or 0 plus 4i in this case. Connecting that with my origin, so that line there would be the visualization of our kind of imaginary number. So we can see, well, the line is 4 units long, so r, in this case, is going to be 4. So that's a nice and easy one to do. And we know the argument, so this here is the positive section of the real axis. The argument is going to be the angle between that section and our imaginary number. And this here is 1/4 of that. So that's actually going to be 90 degrees, isn't it? And remember, 90 degrees, because we're dealing with radians, that's going to be 1/4 times 2 pi, which is, so that's pi over 2, isn't it? So that there is our argument, pi over 2. So that angle there, pi over 2. So we've now got the argument. So putting that as the complex form, that's going to be 4 cis, and then the argument pi over 2. And finally, we're on the last of those easy questions, which is going to be C over here. So this one's going to be a bit trickier. We can't just visualize this one. We're going to have to do a bit of math. But 2 plus I guess first point is, let's plot that on a graph. So we're going to go across to 2 and then up to I. So our rectangular form point is going to be up here. So that there is 2 plus I. Connecting that to my origin, that there is the visualization of that. So the issue here is, because the line's on an angle, we can't just look at the length here. We've actually got to do a bit of math here. But what we're going to do is, if we create a right angle triangle like this, we can do a bit of math, we can do a bit of trigonometry, a bit of Pythagoras' theory to find out that angle and the length. So let's draw a bigger version of that triangle down here so we can work on it. So the argument is going to be this side here. That's because it's going to be the difference from the x-axis up to the imaginary number. So that's all good. And the r value is going to be this long side of the right angle triangle. And I know the base of the triangle is 2 because it's 2 units wide. And the height is going to be 1 because it's 1 unit tall. So with all this information, we can use trigonometry and Pythag to find out the numbers. So let's start off with r. So r, using Pythagoras' theory, a squared plus b squared will be equal to c squared. So a and b are going to be 1 and 2. And then c is going to become that r. So that's going to be 1 squared plus 2 squared is equal to r squared. Oh, I've written c squared, but that's meant to be r squared. So 5 is equal to r squared. So r is going to be equal to root 5. You can convert this to a decimal number. Whatever that might be, slightly more than 2, but you don't need to do that. You can leave it as just root 5. So our length is the square root of 5, however long that is. Now using trigonometry, I can find out the internal angle here. So this side here is the hypotenuse, which we don't care about. This side here is the opposite, which we do care about. And this side here is the tangent, also the adjacent. So we're using tan here, so finding that. So that's going to be tan angle equals O over A. Tan angle, so the angle stays the same because that's what we're trying to find out, and that's going to be equal to 1 over 2. So the angle will be equal to 1 over 2. Oh, sorry, it'll be inverse tan, won't it? So it'll be tan minus 1 of 1 over 2. And plugging that into the calculator, I got 0.4637. I now rounded that to 4 decimal points. So I've now got my modulus and I've now got my argument. I can put that into polar form. So my polar form down here is going to be root 5 cis, and then it's going to be 0.463. So we're now onto the first of the medium questions, and these are going to get a bit messy, so we're probably going to have to do one per slide, and I kind of delete all the stuff in between. But let's start off with plotting the rectangular form over here. So negative 2 is going to be down here, and then it's going to be, negative 2 in terms of real numbers will be up here, and then it's going to be up to positive 3i. So we need to figure out the imaginary number kind of sitting up here. And when we do this, so we're going to connect this over here. Again, we can't see how long it is, and we can't clearly see that argument or that angle kind of sitting in between here and here. So what we need to do, yet again, we need to form a right angle triangle. So I'm going to draw it down here so we can have a bigger version of it that's a bit more clearer. So we've got this angle up here, that angle there, plus this kind of right angle down here is going to form the argument. I'll get to that shortly. So that there is going to be the argument, and that there is going to be the modulus, how long it is. We know it's 3 high, and we know it's 2 wide. So using that information, we can find out r, we can find out the angle, and then using that kind of pi, half pi stuff I chatted about before, we can then get to that final answer. So let's get into that. So dealing with r first, so that's going to be Pythagoras' theory. So a squared plus b squared is equal to c squared. A and b are going to be the 2 and the 3, and c is going to become that r. So 2 squared plus 3 squared will be equal to r squared. So r squared, I've written r cubed, r squared is equal to 13. So r will be equal to root 13. We can now do the same with our inverse trigonometry. So it's normally tan, but let's just check to make sure. So that's the opposite, that's the hypotenuse. We don't care about the hypotenuse, and again that's the adjacent, so I'll leave the a there. So yep, definitely going to be tan. So let's calculate the angle there. So tan angle is equal to O over A. Tan angle is equal to 2 over 3 in this case. So the angle inside that triangle will be equal to tan inverse or negative 1 of 3 over 2. So I just want to note this angle here comes to, what was that on my calculator? So 0.5882, and that there had a 4 dp rounding. So this angle here is really, really important to understand. This represents the angle inside the triangle, but up the top of the here, that's not the argument. So the argument is the angle inside the triangle, which is over here, plus the half pi. So my actual argument is going to be equal to 0.5882, forgive the messy handwriting, plus pi over 2. And when I put that in my calculator, I'm getting 0.159, and that there had a 3 dp rounding. So now that I've got r, now that I've got the argument, I can plug that into my polar form formula to get the answer. So down the bottom, I'm going to write it down. So my polar form answer will be root 13 cis 2.159. So we're now on to the B medium question just over here. So the first thing we're going to do, like we've done with the other questions, we're going to plot our rectangular form. So we're going to go across to negative 4, which is the real number, down to negative 3i. So this point over here, connected to my origin, that there is the imaginary number we're trying to deal with here. And like we've done with the other questions, we kind of connect to make a right angle triangle. We're going to be able to find out this angle here, and we need to be able to find out the length of it. The width of this triangle is 4, and the height of this triangle is 3. So I guess let's just get straight into this. So let's start off by calculating r using Pythagoras' theory. So a squared plus b squared will be equal to c squared. A and b are 3 and 4. You might also remember this triangle, quite a famous one as well, r squared. R will be equal to root 25. So the length of this line, 5 units long. So that was nice and easy for that. There's no surd here because we're able to simplify it as well. So the next step we need to do is the trigonometry, and most of you hopefully have spotted now it's almost always tan. Oh, sorry, I think it's always tan for this one here. So O over A. So make sure you get them the right round. This is the only way you can get it wrong. So opposite this, that's my opposite. There's my adjacent. So it's 3 over 4 in this case. So to be tan angle is equal to 3 over 4. Moving it to inverse tan, so that's going to be inverse tan of 3 over 4. And plugging that into my calculator, I got 0.6435 as my angle. And again, same thing as the other triangle. So this is the angle inside the triangle. It is not your argument. So the argument, to clarify or to recap it, so this is the part of the x-axis we're looking for. The argument is the angle starting from here all the way over there to your angle. So it's going to be the angle we calculated here plus the pi, which represents this and this quarter here. So to find the actual argument, it's going to be 0.6435. I'm going to add on my pi, and that there will be equal to 3.7851, and that there was my 4 dp rounding. So I've now got all the information I need. I can put it into polar form. So my answer is going to be 5 cis 3.7851. We are now on to question C from the medium ones. Let's plot that down. So we're going to go across to positive 1, down to negative 5i. So it's going to be quite a skinny triangle. So that one's over there. Our modulus will be that line connecting there. And if we made a right angle triangle, we could probably make this one here as well. So let's kind of sketch that over here. That way we can see it a bit better. So my triangle would have a width of 1 and a height of 5. The angle up here would be relevant to finding the modulus. Again, that angle there is not the modulus itself. It's just an angle that we'll use later on to calculate it. And that hypotenuse we'll be able to find the R value with. So let's start off with R. So we've caught on quick hopefully. That's always A squared plus B squared and C squared. So we're going to have 5 squared plus 1 squared is equal to R squared. So in this case, R will be equal to the square root of 26. Again, I'm going to leave that in its surd form. You can convert that to a decimal if you're wanting to, but you don't need to. So the next step is, let's find out that angle inside the triangle. And again, most of us have figured out it's almost always tan. Oh, sorry, I keep saying almost always. It's always tan. So there's my tan formula. The only way you could get it wrong is by having your opposite and your adjacent the wrong way around. So hopefully you did opposite and adjacent this way around here. I always write them on my diagram just to be short. So tan angle is equal to 1 over 5. Angle is equal to inverse tan of 1/5. And when I plug that into my calculator, I get 0.1974. So I've now got this kind of angle sitting up here on my diagram. So it's quite tough to see. There's a few different ways you can find the argument. So I guess the first thing you could do is you could do this section here, which is 3/2 of pi, and you could add on the smaller bit to find the argument. Or you could do the opposite. This here would be negative 1/2 of pi. Note, because it's going clockwise, and then you could get rid of this angle here. So I'm going to do both of them just to highlight what it is. So let's say you're doing we'll do AC for anti-clockwise. So your argument would be 3 pi divided by 2 plus the angle of the triangle, which is this stuff here. And when I do that, I get 4.9086. The next one, let's say you're doing clockwise. So the angle could be, so let's get rid of that. So it could be the pi minus the angle that we just did. And then remember, that is anti-clockwise, so it'll be the negative answer of that. And when I plug that into my calculator, I got negative 1.3734. So two different answers, and they both are correct. So if you had the anti-clockwise answer, so your answer would be the square root of 26 cis, 4.9098. Or if you did the clockwise answer, again, it would be root 26 cis, and then it would be negative 1.3734, and that's to represent, you've gone in the clockwise direction as opposed to the prescribed anti-clockwise direction. We're now up to the hard questions down the very bottom. Some of them are going to be pretty cruisy, some of them are pretty tough, so let's do 4A. Let's start off with Ki. So again, remember Ki, there's no real element here, so it's going to be 0 plus Ki. And because it's a positive K, it's suggesting it's a positive complex number, so it's going to go up here. So let's just say this here is point K, because that's Ki. So connecting that to the modulus here, we know the line is K units long, so our modulus is going to be K. My argument, the gap between the positive version of the real axis and the imaginary number, well, that's going to be half of pi over 2, because that's 90 degrees. So this one here, looks messy, looks complicated, but it's actually okay. So this one here will be cis, or K cis, pi over 2. Now on to B. The next one here we got, it's just negative C. So again, reminder, so negative C, that would be the real element. So that would be negative C plus 0i. So this is going to be one of those ones. It's just going to be a horizontal line. So because it's negative C, it's kind of suggesting it's on the negative side of the element. So let's say this point here is negative C. Connecting that to the origin, so that's the imaginary number we're dealing with. So we know how long it is. It's going to be C units long. And from the positive side over to here, we know that argument's going to be pi. So putting those together, our polar form is going to be C cis pi. And the very final question, so let's say we don't know either, so let's say it's just kind of x plus yi. So again, it's suggesting both of them are positive. So let's just kind of put a random dot up here. So let's say that's x plus I. So if you make your right angle triangle again, we know it's x units wide and y units high. We are going to do our same calculations with Pythagoras' theory and trigonometry. Instead of being able to calculate an exact answer for either r or the argument, we're going to come up with an expression in terms of x, in terms of y. So let's start off with the modulus. So that's going to become from the Pythagoras' theory. So a squared plus b squared is equal to c squared. So it's going to be x squared plus y squared is equal to r squared. R in this case would be the square root of x squared plus y squared. So that's our expression for r. We then need to repeat for our argument. In this case here, the angle inside the triangle is also the angle that is the argument. So we don't need to do any stuff with the half pi, etc. So let's come up with an expression for that. We know it's going to be in relation to tan. So it's going to be tan angle equals O over A. Our opposite, so that's our argument there. So our opposite's going to be Y, and our adjacent's going to be X. So that's going to be tan angle is going to be equal to Y over X. And then that's going to be inverse tan, right? So tan minus 1 of Y minus X. So again, it's a bit messy, but we've got an expression for the argument in terms of Y and in terms of X. So let's plug that in to our final form. So my modulus is going to be x squared plus y squared of cis, and my argument will be tan minus 1 of y divided by x, and so that wraps up this question. So hopefully you found this video really useful. I know it took a while to listen and get them all done, but hopefully you can see the type of question you're struggling with, and hopefully they all make sense. So thanks so much for watching. Keep an eye out for some more calc videos to help you out throughout the year.